Go ahead and get started. Tatsumi, everyone. My name is Althea Walker. I am Nez Perce, Hopi, and Gila River, and the Director of Community Resilience for the Climate Science Alliance. We really appreciate you all joining us today to learn about this work, to listen from our good friend Kevin Solon from KRS Environmental Consulting. We've had the chance to work with Kevin over the last, I don't even want to say few years, it's been more than a few. Um, and I really appreciate the funding and the support from the National Forest Foundation. But today, Kevin will be sharing with us a presentation titled Listening to the Forest, Tribal Stewardship and Modern Technology, How We Define and Interact with Forests Through Sorry, this isn't my way. Drone imagery and mapping techniques. And this sharing this information, this work that has been going on for many years, is part of the Climate Science Alliance's Stewardship Pathways program, where we work closely with partners and communities in collaborative and cooperative stewardship and conservation to build capacity, support economic and workforce development, to advance co-stewardship for all ancestral lands through the various training pathways that we have. So we really appreciate you all taking this time. We appreciate Kevin taking his time. You know, we have spent many hours preparing for this. So thank you so much. We appreciate you joining us today. Just we ask that you open up your heart, your mind, to this work, to this learning opportunity, and we appreciate you all in joining us. So I'm going to pass it over to Kevin to introduce himself and to learn more about the work that he's been doing.
All right. Thank you so much for that nice introduction, Althea. And hello, everyone. I'm Kevin Solon. Thank you so much for being here today. I know the audience is quite diverse, so I really appreciate the range of experience that's in the room today. Today, I'm here to introduce and discuss the Physiospatial Monitoring Program, which is at its simplest a decision-making tool that land managers can use to see, measure, and communicate change on the land more clearly. The presentation blends personal story, my forestry background, and long-term data collection. And the goal is to demonstrate how technology can add another layer of observation, one that helps us um, listen more carefully, document more clearly, and help land managers make data-driven decisions. Two quick side notes is one that much of this presentation was prepared with Clip-it and screenshots. It's very well put together, but if there's any hazy or blurriness to it, it's because of that. I'm not a videographer. And second, although there is a big tribal theme to it, due to the sensitivity of the data that I'm collecting, much of this is actually going to be showcased at the Girl Scouts Camp Winnetka, located by Julian, and not so much because of the privacy, but because the Girl Scouts really have a lot of different features and changes on the landscape that I've been able to measure over the last 3 years. So when it comes to demonstrating to you what this technology can do, it's actually best showcased from the Girl Scouts. Okay. So now I'm going to share my screen. Okay, so that should be up now. Good to go. Okay, I drag this over here. So, okay, well, I want to begin by locating myself. My father's side of the family comes from Solent, Norway, and my mother's side is German. My family later settled in the Northern Plains, a region shaped by tribal nations with deep and continuing relationships to land. I share this because much of my work today occurs on tribal reservation lands, and I want to be clear about the perspective I bring. I'm not opening with lineage as a credential. I'm opening with it because place, responsibility, and relationship matter in the care of living spaces. Should say living landscapes, not promoting a business. Okay. So this is my great-great-grandfather, Nels Magnuson. He was a pioneer and a legislator whose work centered on the idea that people who live on and work with the land should have a voice in decisions that affect that land. I share this not to equate my family history with tribal histories, but to explain part of the value system I bring into this work, which is respect for place, local knowledge, self-determination, and stewardship. That matters because the tools I'll discuss today, drones, GIS, vegetation indices, and tree level monitoring, they're only tools. They should support the people and communities responsible for caring for the land, not replace their judgment. So before forestry, I worked in the oil field. I was good at the work, but also knew I didn't fully belong there. One day, someone I respected, and even though I didn't particularly like him, told me something direct. And he said, Kevin, you're really good at this job, but you don't fit in here. You're still young enough to make a change in your life. Don't wait until you're too old to move. And that really stuck with me. Excuse me. Within a month, I went to Monterey on a solo vacation and met someone selling a sailboat. The reason he was selling it was that he was going to school at Humboldt State University. I bought the boat, lived aboard for about 14 months, and worked at a wine estate. Absolutely loved that time in my life. But after about a year, I finally heard something my dad had been saying since I was about 12 years old. Have you thought about going to school for forestry? He had said it for over 2 decades, but there's a difference between being told something and being ready to hear it. Within a month of finally hearing my dad, I sold the boat, and within a year, I was at Humboldt State studying forestry. That decision eventually led me to my research in forest restoration, individual tree response, and the monitoring work I'll share today. So I'm starting with my own story because it shaped how I approach this work. In my own life, I had to become ready to hear something that had been in front of me for years. In this presentation, the goal is similar: to use field observations, research, and technology to better hear what the forest has been telling us all along. So my research foundation includes peer-reviewed work published in Forest Ecology and Management, and that was focused on forest response to restoration treatments. And that work gave me a foundation in measuring how forests respond over time. My current work builds on that foundation by applying drone-based monitoring and individual tree crown analysis to track vegetation condition and treatment response at the tree level. After graduate school, I moved down here to San Diego. I had been studying redwood forests, so my idea of forestry was shaped by big trees, dense canopies, and North Coast forest systems. Then someone from CAL FIRE down here said something that stuck with me. And he said, down here, we don't manage forests, we manage brush. Now, I understood what he meant, though I took it figuratively. Southern California really forced me to think about forestry more broadly, not just as trees, but as vegetation, fire, infrastructure, wildlife habitat, fragmented land ownership, and community safety all overlapping on the same landscape. And that became the question for me. How do we monitor vegetation and treatment across places where ecological risk, public safety, and stewardship decisions all intersect? Okay, so with that context, here's the path we'll follow today. I'll start with traditional forestry and some of the current challenges facing forestry programs. Then I'll introduce the visuospatial monitoring program as a decision support tool. And from there, we'll cover how visible and invisible light help us interpret vegetation condition, including a short ArcGIS demonstration with multispectral imagery. We'll also talk about the limitations of drone data and why field physiology measurements are important. Then we'll move into tree spacing, use cases, and how these data sets can be viewed in an interactive cloud-based environment by any of you. So, and then I'll close with next steps and how PSMP could potentially support the work many of you are already doing. All right, getting used to this. Okay, so my background brings together arboriculture, forest health, field operations, and drone-based monitoring. ISA, the International Society of Arboriculture, credentials arborists and tree care specialists. And those credentials are relevant because much of this work happens at the individual tree level. Okay, let's briefly run through the traditional forestry framework that many land managers already know. Traditional forestry is powerful. It gives us field-based measurements, long-established metrics, and models for understanding forest structure and growth. But it also has limits, especially when we need to communicate clearly with communities, legislators, funders, or partners who are not trained in forestry. One of the basic measurements in forestry is DBH, diameter at breast height. A forester measures the diameter of a tree trunk at a standard height above the ground, so 4.5 feet. DBH is simple, it's repeatable, and useful. It helps describe tree size and becomes the basis for many other calculations. From DBH, we can calculate basal area. And basal area is the cross-sectional area of a tree stem. The formula looks technical, but the idea is pretty simple. It converts tree diameter into the amount of growing space that particular tree occupies. It's one of the main ways foresters describe density. One way to think about basal area is like real estate. In a city block, houses occupy space. In a forest, trees occupy growing space. And basal area helps us understand how crowded a forest is and how much competition exists for light, water, and nutrients. Foresters may also measure tree height. Height helps describe tree growth, site productivity, and stand structure. And together with diameter, it tells us more about the tree than diameter alone. Crown ratio is the proportion of the tree's height that has live crown. So a tree with a larger live crown often has more photosynthetic capacity, while a very small crown can indicate suppression, stress, or competition. But like all field measurements, it's useful, but it still has to be interpreted in context. So field crews also look for visible defects, so cavities, cracks, broken limbs, decay, or other signs of structural concern. And these observations are important because they connect forest measurement to real-world risk, safety, and management decisions. This is also where field knowledge matters. A model can organize information, but people still need to understand what they're seeing on the ground. Well, after collecting field measurements, foresters often use models like the Forest Vegetation Simulator produced by the U.S. Forest Service to estimate forest structure, growth, and treatment outcomes. And these models are valuable, but the outputs can be dense and difficult to communicate to a broad audience. And that creates a challenge. If partners, legislators, or funders cannot understand the results, then even good data may fail to support good decisions. Okay, so traditional forestry is valuable, but Agencies today are now responsible for overseeing billions of dollars in public investment for forest health, fuels reduction, and carbon projects. That level of investment requires more than technical reports. It requires usable data, repeatable monitoring, transparent reporting, accountability, defensible evidence, and clear communication. When I say repeatable monitoring, I mean a way to document baseline conditions, implementation, and validation. What was there before, what work was done, and whether the outcome matched the objective. My monitoring framework is designed to bridge that gap, not by replacing traditional forestry, but by adding visual, spatial, and repeatable information that helps stakeholders understand what is happening on the land. And those challenges are exactly why I developed the Physiospatial Monitoring Program, or PSMP. So at its core, PSMP brings together three things: tree physiology, tree spacing, and repeatable monitoring. So tree physiology is about the tree's biological signals, so chlorophyll, water stress, and overall vegetation condition. Tree spacing describes where trees are located, how crowns are arranged, how dense the stand is, and where competition or ladder fuels may exist. Monitoring is about repeating those measurements over time. So we're not just looking at one snapshot, we're watching change. The value of PSMP is in the overlap between these three areas. Where physiology and spacing overlap, we can attach biological condition to individual tree crowns. We can ask which trees are showing stress, what species are they, where are they located, and what conditions surround them. Where physiology and monitoring overlap, we can track whether those biological signals are improving, declining, or staying stable through time. That helps us evaluate treatment response, environmental stressors, and long-term forest health. And where spacing and monitoring overlap, we can document structural change, which trees remain, how spacing changes after treatment, where canopy gaps form, and whether fuel conditions are moving in the intended direction. At the center is the real goal. Each tree becomes a trackable biological unit with a location, a species, a crown, a condition signal, and a history. And that's what makes PSMP useful for field verification, treatment evaluations, reporting, and management decisions. This is the drone I use. Its name is Ricky T. It was named in honor of a forestry crew member at Palma who passed away not long before I purchased it, which was 4 years ago today, actually. And it was 6 years ago tomorrow that I defended my master's thesis. So this time in April, it is typically a big month for me. The aircraft is a Wingtra Gen 2, which is a blue UAS listed platform. And that matters because it supports work where data security and government compatibility are important. So I did not want this tool to feel like just another piece of equipment. Naming it was a way to carry memory and respect into the work. Today, Ricky T flies above his homelands collecting data for the Physiospatial Monitoring Program. And the photo on the right shows Ricky T in front of cultural fire. This is a rare and meaningful image. A modern monitoring tool sitting beside one of the oldest land stewardship practices. And to me, that captures the purpose of PSMP, not replacing cultural knowledge or field experience, but adding another layer of observation that can support management decisions. So this is a stitched image of a forest site. We call it an orthomosaic. It's essentially many overlapping photos combined into one accurate image. And it was collected by Ricky T. So At first glance, it looks like a simple aerial image, but this is the foundation for everything that follows. It gives us a spatially accurate view of the site and lets us see the arrangement of canopy. We see openings, roads, and vegetation patterns across this landscape. And this is where the monitoring process starts, with a clear record of what is actually on the ground. The next step is where the image becomes actionable. We're no longer looking at this area as a single green mass of canopy. We're breaking it into individual trees and forest features. Each polygon becomes a discrete monitoring unit that can be tracked, measured, and analyzed over time. That shift matters. So instead of saying the canopy changed, we can ask which trees changed. Where are they? What species are they? And how are they responding? So instead of saying this area is 15% drier, we can begin identifying individual trees that show measurable change. So for example, tree number 8,491 may show a water index shift approaching a predefined alert threshold that we set in the computer. That is not a diagnosis of the cause itself, but it tells us which tree or trees deserve closer field observation. This is the basis for individual tree analysis and for building what is essentially a digital twin of the forest. This slide adds another layer to the map. The polygons are still individual trees and forest features, but the legend now uses traditional names alongside the scientific species codes. And that matters because this is not just a technical data set. It's a stewardship data set tied to place, language, culture, and tribal sovereignty. And I want to be clear, the tribe owns this data. My role is simply to collect it, analyze it, and turn it into tools they can use for land management. The data doesn't belong to me, and the decisions do not belong to me. Using traditional names is one small way to make sure the map reflects the people and place it represents. It moves the product away from being only a Western scientific inventory and towards something more useful for tribal natural resource management, forestry departments, education, and long-term stewardship. So when we talk about PSMP, we're not just talking about mapping trees, we're talking about building a monitoring system that respects tribal data sovereignty and supports the people responsible for caring for the land. All right, before I talk about drone imagery, I want to spend a few minutes on how light works. The main idea is simple. Our eyes only see part of the light reflected from the forest. The drone sensor measures more of that reflected light, including wavelengths we cannot see, and that gives us clues about tree health. Human eyes are excellent at interpreting visible light, but visible light is only a narrow slice of what is reflected from the forest. We mostly perceive color through three photoreceptors, roughly blue, green, and red. That gives us a useful view of the landscape, but it leaves out wavelengths that plants reflect beyond what we can see. And those invisible wavelengths can tell us a lot about vegetation condition. This is the electromagnetic spectrum. The important part is that visible light is only a very small part of it. Human vision operates in that narrow visible range. But just beyond visible red is near infrared light, and that is where vegetation reflects a lot of useful information that our eyes can't see. So this small area just beyond visible red is one of the most important parts of the spectrum for vegetation monitoring. Again, human eyes stop at visible red, but vegetation continues reflecting light beyond that range. And red edge and near infrared sit just beyond what we can see, and those bands are what help us detect vegetation signals that standard imagery can miss. Chlorophyll captures light for photosynthesis. It absorbs much of the red and blue light and reflects more green light, which is why leaves appear green. When chlorophyll declines, leaf reflectance changes. A standard RGB image may only show that change after it becomes visible to our eyes, but red edge and near infrared bands can help detect earlier shifts in vegetation condition. And leaves do not reflect all light equally. Moving just beyond red, the reflectance rises quickly through the red edge. Then, in the near infrared, healthy leaves often reflect strongly because of their internal leaf structure. That is why red edge and near infrared are so useful. They're not magic health detectors, but they are sensitive to changes in chlorophyll, leaf structure, and water stress. A tree may still look green in a standard photo, while its red edge or near infrared response is already changing. This is the red edge P sensor I fly on the Ricky T. A standard RGB combines blue, green, and red light into one natural color image. The red edge P camera records those visible bands separately, but it also records red edge and near infrared bands beyond human vision. That separation is what allows us to analyze tree condition instead of relying only on what the forest looks like to our eyes. So before we get into multispectral imagery, I want to quickly ground this in something familiar, how a normal color image works. So this NASA image shows the same hot air balloon separated into red, blue, and green channels. Each channel is measuring a different part of visible light. By itself, each one is just a grayscale image showing how strongly that color is being reflected. But when red, green, and blue channels are blended together, we get the natural color image on top, the image our eyes see. Okay, and so now time for a video demonstration. Here, this would be the easier way of doing it. Yeah, so I figured this would be, this best way to present this section would be as though you're sitting next to me at my computer rather than showing a series of slides. So it may be a little lag, but this way will be far better. The file sizes are massive and range from 30 to 50 gigs each. Make sure that's playing. Yep, okay. So I'm starting here with the RGB image collected with the MAP 61 camera, so not the multispectral. It looks a little rough around the edges, but I actually just pulled this out of cold storage last night. This is a high resolution mapping camera designed for very detailed aerial imagery. And some of the features we can see, and this is Camp Winnack at the Girl Scouts. There's a watercourse buffer, we got structures identified, and then of course management treatment units. So Wintra came out to Camp Winnack in 2024 and tested this camera. The detail is super impressive. As I pan across the camp, you can see why this type of imagery is useful for situational awareness. We can see in stunning detail the helicopter landing pad, roads, structures, and the emergency animal shelter, and the vegetation surrounding those assets. The imagery is also great for photogrammetry and 3D reconstruction, where software can use overlapping images to build detailed digital surface models. But for this demonstration, we're just going to focus on the 2D because that's the most practical way to show how these data can support you. Even without going too deep into 3D software, the 2D gives us a very powerful foundation. And we're scrolling over to the ear curtain burners. The Girl Scouts purchased these, I think about 2 years ago. And this is how they're disposing of their infested wood. It's both an art and a skill to learn how to use those things. The full 3D reconstruction workflow can also be taken into specialized software platforms. Those tools are super powerful, but they're not the focus of this demonstration. So we're going to actually skip over that. Okay, so now we're going to change cameras. I'm going to turn off this image and then turn on the Red Edge P image, the multispectral camera. So the image that we're looking at now was captured in 2024, and we're starting with what the RGB bands look like through the Red Edge P. Its resolution is much lower than that of the other camera, but what's cool is we got 5 bands to work with, so right. So, and this is where the false color really is going to become useful because with false color, we can place an invisible band like near infrared or on one of those visible channels you see in the upper right. Here's our demonstration polygons for the day. All right, so, all right. So in the symbology panel in the upper right corner, you can see how the channels are currently set to their natural positions, but now all assign near infrared to the red channel, red to the green channel, and green to the blue display channel. So the colors we see on the screen are no longer natural. This is a false color composite. The forest is not actually turned red or pink. We just shuffle the different light bands around from the Red Edge P camera. So settings can be adjusted many different ways. I don't even know how this is looking on your end, but again, this is just for demonstration purposes. And this toggle here is to show you the accuracy of the map. So just keep your eye on the helicopter landing pad. So even across multiple data sets, that the imagery is very precisely grounded. So healthy, dense vegetation usually reflects strongly in near infrared. So it often appears bright red or pink, such as in this view. Areas with weaker vegetation response, bare ground and roads and structures, and shadows tend to look darker or more muted. The value of this view is that it helps us see vegetation differences that may be subtle or invisible to a standard RGB image. Again, it's still a proxy, it's not a diagnosis, but it gives us another useful layer of information. And okay, so next I'm going to switch to a different false color composite, one that emphasizes the red edge portion of the spectrum. Do that automatically there. In this view, I'm assigning near infrared to the red display channel, red edge to the green display channel, and red to the blue display channel. You can see that in the upper right corner there. So the reason this matters is that the red edge is the transition zone between visible red light and near infrared light. Plants absorb a lot of visible red light for photosynthesis, but they reflect much more strongly in near infrared. The red edge sits right between those two behaviors. And that makes this band especially useful for vegetation work because subtle changes in chlorophyll content or plant condition can begin to show up here before they're obvious in a standard RGB image. So again, these colors are not natural. We're rearranging the bands to make the plant differences easier to see. But the value of this composite is that it gives us another perspective on canopy condition. So now I'm displaying only the near infrared band by itself, no longer a color image. It's showing how strongly different surfaces reflect near infrared light. Healthy, dense foliage reflecting strongly, while declining crowns may appear darker or thinner or less even. Still just a proxy, but gives us a quick way to see canopy differences. All right, the fun part's coming up here. Okay, so EVI, or Enhanced Vegetation Index, helps measure vegetation vigor using the red, blue, and near infrared bands. It's especially useful in areas with dense canopy because it reduces some of the background noise. Um, let's see, for the final view, we're moving from visual interpretation into a vegetation index. This is an EVI time series from 2023 to 2025. Right now, I'm toggling between 24 and 25, although it really doesn't look evident except on the outer edges. Apologies for that. Um, but now we're going to zoom into the demonstration individual tree crown polygons and toggle between those years. And then to keep toggling to a minimum, I'm going to keep the same RGB base map you see the same, even though I'll be toggling among the 3 years. So this is where the time series starts to become useful. Because the crowns are isolated and the shadows are filtered, the comparison is much cleaner. So that's 23, right when they did some work. And then that's 2024, and that was 2025. So we can see, signs of improved crowns, a signal stronger and more continuous, um, rather than broken and weak like it was earlier. So that's 23 again, I believe. Now I've lost my order. So coming up on 2024, showed a really good response, but there's a lot happening behind the scenes here to clean the data, align the imagery, and filter out the noise and keep the comparisons fair. I'm not going to unpack all of that here, but the important point is that the output is designed to be repeatable. So after looking at RGB, multiple false color composites, and now EVI across 3 years, the story's pretty consistent. The tree crowns are showing measurable change, measurable improvement, and the imagery has given us a practical way to track that change over time. So now I zoomed in a bit. I just threw this in this morning. Showing 1 year overlaid from the other. So this you should be able to see differences between the 2 years. And the ground is going to look a little bit more red because it's a difference after treatments were done and the ground filled in. It's not as reflective. Should have moved it a little faster, but then here's what we're seeing underneath is the RGB imagery from between the 2 years, 2024, before any work had been done, and then 2025 after the work had been done. And this is where drone-based multispectral monitoring becomes powerful. We're not just seeing the landscape, but we're actually measuring how it's responding. Okay. So this is just a little bit of a cleaner way to show you that, because now that you have a good idea of what you're looking at. This is a treatment monitoring example from an area affected by the gold-spotted oak borer. Thinning and mastication were applied in early 2023, around the time this first image was collected. In fact, it was like the day they were working on the day I collected that. And the panels show the same canopy area across 3 growing seasons, 2023, 2024, and 2025. And so through this false color view, stronger pink and red tones generally indicate a stronger vegetation signal. And by 2024 and 2025, the canopy response appears stronger and more consistent suggesting improved vigor in the remaining trees after the treatment. So this does not prove recovery by itself, but it gives us a repeatable way to track treatment response over time. And seasonality likely factored into the 2023 panel. If you can tell, the overall color doesn't quite match up with 24 and 25, but all settings in ArcGIS were the same, standardized. So this slide is important. This shows NDRE, which is normalized difference red edge, so a little bit different than EVI, what you saw earlier, applied to individual Quilla crowns. And Quilla is California black oak, or Quercus calogi. The reddish polygons in the upper part of the image are trees in an area treated about 2 months before this image was collected. The brighter green polygons on the right are trees in an area that was treated about 2 years earlier. And then the darker untreated area on the left and bottom center provides control for a comparison. And those aren't shapefile lines, that's PowerPoint drawing. So what we may be seeing is a release response. In dense conditions, trees can be suppressed by competition for light, water, and growing space. After treatment, the remaining trees may move into a more resource-enriched environment, which can appear over time as stronger vegetation signals in indices like NDRE. However, one image does not prove recovery. PSMP uses repeated flights in multiple vegetation indices to quantify change through time. In this case, we track Quilla across treated and untreated areas to detect sustained tree level shifts and prioritize trees or areas for ground observation. All right. I hate to say this, but there are limits to aerial imagery. It's still useful and powerful, but the drone is flying about 300 feet above the canopy, so it's not directly measuring tree physiology. It's collecting reflected light data, which means the outputs we generate are essentially visual proxies for health. They're useful and powerful, but by themselves do not tell us the full biological story. So to strengthen interpretation, we have to pair the aerial imagery with data collected on the ground. So this slide shows where we're at in the PSMP workflow. We've already talked about the aerial baseline and collecting drone imagery, precision mapping, and where we convert canopy into individual tree crowns. Now we're moving into the physiology phase, number 3. By collecting actual tree phys measurements, we can begin assigning biological meaning to the patterns we see from above. So in other words, this is the step where PSMP starts moving from this tree looks different to this tree may be experiencing a measurable physiological change. Before we begin, I'm going to explain the biological circuit we'll be discussing, and I'll recap this at the end. So water directly influences photosynthesis. Photosynthesis directly influences tree growth. Tree growth directly influences understory plant diversity, and plant diversity directly influences wildlife diversity. Water potential helps us understand tree stress before it's visible from above. The drone can show us patterns in canopy reflectance, but instruments like stem psychrometers and pressure chambers help us connect those patterns to what is actually happening inside the tree. I use both stem psychrometers and pressure chamber measurements in my published research, so this part of PSMP builds directly on that foundation. The goal is to pair aerial signals with field physiology so we can interpret canopy change more defensively. While water potential tells us about stress, photosynthesis tells us if a tree is making food for itself. Lycor loaned me an LI 600 instrument to test out in the field, and CAL FIRE's TWR program managers were there during one of those demonstrations. It was a terrible day for flying the drone, but I was still able to demonstrate how the instrument works and how leaf level measurements can support the aerial side of PSMP. And the photo on the right shows a canyon live oak being measured with that instrument. Before we move into dendrochronology, I want to bring us back to basal area. If you remember, basal area tells us how much growing space a tree occupies, but it also connects directly to growth. As a tree adds wood each year, its stem gets wider and its basal area increases. That annual increase is called basal area increment, or BAI. By measuring tree rings, we can track BAI through time and see how a tree responded to drought, competition, treatment, or other environmental stressors like fire. Think of this green circle as the tree's basal area at the start of the year. It represents the cross-sectional area of the stem as measured at breast height. So in other words, this is the amount of growing space the tree currently occupies. The yellow ring is the new wood added over one growing season. That annual increase is what we're referring to as basal area increment, or BAI. So basal area tells us how much space the tree occupies. BAI tells us how much that tree grew. Boom, boom. Dendrochronology is the scientific method of precisely dating tree rings. Each ring represents a year of growth, and the width of that ring tells us something about how well the tree grew that year. Wide rings generally indicate better growing conditions, while narrow rings can reflect competition, environmental stressors, or other limiting factors. When we convert those ring measurements into basal area increment, we get a growth record through time. That lets us ask, when did the tree grow well? When did growth slow down? And how did it respond over time? This gives PSMP a long-term memory layer. The drone shows us current canopy condition. Physiology measurements tell us how that tree is functioning now, and tree rings can help show how that tree has responded over years, decades, or even centuries. And as a side note, you can see the alternating light and dark bands. The lighter, wider bands are early wood, formed when the tree is growing quickly early in the season. The darker, narrow bands are late wood, formed later in the growing season as growth slows down. If you look at the picture in the lower right corner, one light band and one dark band represent 1 year of growth. Okay, I've prepared you. Here we go. So this graph comes from my published research. So we just talked about BAI is the amount of new wood the tree adds each year. So in simple terms, this graph is showing how much new wood these trees were adding over time. Arrow 1 marks a thinning treatment in 1978. After thinning, we might expect the remaining trees to immediately take off because they have more light, more water, and less competition, but that doesn't happen right away. The stronger growth response does not clearly appear until several years later, closer to arrow 2. And that leg is important because it tells us that response is not always immediate when we measure it through stem growth alone. The trees have been responding biologically before it became obvious in basal area increment. This is the part of the graph that interests me the most, the space between treatment and the clear response. The treatment happened at arrow 1, but the tree did not clearly show that response and growth until years later. So the question becomes, what was the tree doing during that gap? It may have been expanding its root system. It may have been building canopy. It may have been adjusting to new lighting conditions, water availability, or reduced competition. It may have also been recovering from release or thinning shock. Traditional dendrochronology is powerful because it gives us the long-term record, but it often doesn't tell us the story until after several years have passed. And PSMP is designed to help observe that recovery window while it's still happening. By combining drone imagery, tree physiology measurements, and repeated monitoring, we can begin detecting short-term changes before they become obvious in the tree ring record. So tree rings tell us what happened, and PSMP helps us watch it happen. Once water status, photosynthesis, and growth change, the forest structure changes too. That affects light, moisture, and growing space near the ground. Understory surveys help us understand whether those changes are supporting a more diverse plant community. So this adds another biological layer to PSMP, not just how individual trees are doing, but how the vegetation community is responding. The final layer is wildlife. If previous metrics we just discussed change, then wildlife habitat changes as well. Cameras and field surveys help us understand species presence and diversity over time. This gives us a more complete picture of whether forest treatments are supporting ecological function, not just a changing canopy structure. So this is the biological circuit behind PSMP. And once again, if you studied the symbols, you might know this. Water potential directly influences photosynthesis, and photosynthesis directly influences tree growth, and tree growth directly influences plant diversity, and plant diversity directly influences wildlife diversity. So these symbols may have looked technical at first, but now you've seen each part. This does not require an army of people. Some parts require specialized equipment, but the workflow is repeatable, relatively efficient, and scalable for the amount of information it provides. So the goal is not to make monitoring more complicated, but connect these biological signals to one practical framework that helps us understand how ecosystems respond through time. In other words, PSMP is designed to turn scattered measurements into a connected biological story. So we've just talked about the biological side, and now we're going to shift to tree spacing. And this is where we look at where trees are located, how crowns are arranged, how dense the stand is, and how treatments change the structure of the landscape. Tree spacing matters because spacing affects competition, fire behavior, and wildlife habitat. Most projects are still tracked with a handheld Garmin. They're great tools. They can help you get back to your truck, which is important. But if the unit is accurate to plus or minus 12 feet and the equipment is about 70 inches wide, the GPS error is bigger than that of the equipment doing the work. And that's fine for navigation, but it's not fine for documenting activity acres. And accuracy matters because contractors always work in straight lines, which is to say they absolutely do not. They get rocked out, they get sloped out, pushed around by terrain, but acres treated are acres treated. The issue is that handheld Garmin units often are not accurate enough to capture the true footprint, especially when the machine itself is only about 70 inches wide. With drone imagery, we can map the actual treatment edge instead of a rough estimate. This is the kind of spatially accurate shapefile that agencies like CAL FIRE can actually use. These layers can be delivered on time, uploaded into systems like Survey 123, and used for GIS-based project tracking and quarterly reporting. Once the treatment footprint is in a geodatabase, it also becomes possible to connect acres treated directly to grant dollars, prescriptions, contractors, treatment dates, monitoring results, and reporting requirements. So this is not just a map. It becomes a defensible project record where the work happened, how much was completed, and how that work ties back to funding and implementation. This is a before and after example of treatment verification. The yellow points represent tagged vegetation, and the orange polygons represent retained wildlife habitat patches. On the left, we see pre-treatment conditions. On the right, we see the post-treatment condition after implementation. The value here is that we're not relying only on a written description or a rough GPS track. We can visually and spatially document what changed. This allows us to quantify spacing, confirm retained patches, map the actual treatment footprint, and provide funders or agencies with defensible evidence that the work was implemented. So this is a simple example of how PSMP can support verification. So these results were submitted to the project funders, Climate Science Alliance and National Forest Foundation. Thank you for funding this as part of their full implementation report. I'm only going to show an excerpt here, but the point is that we're able to quantify whether the scope of work was actually implemented on the ground. These two numbers are telling different parts of the story. The percent meeting the 25-foot target tells us how many trees crossed the management threshold. The median nearest neighbor distance tells us how far the typical spacing shifted. Within the matrix where the work was done, a lot of vegetation was moved closer to or just over the 25-foot target. So the percent meeting the objective nearly doubled, even though the typical spacing increased by 3 or 4 feet. So think of this like a test score. If the passing grade is 70% and a lot of students move from the 60, 66 to 69% up to 70 to 73%, that pass rate can jump dramatically, even though the class average only rises a few points. In the retained patches, spacing stays essentially unchanged, which is what we wanted because those patches were intentionally left clustered for wildlife habitat. So the takeaway is simple. The treatment widened spacing where it was supposed to and preserved patch structure where it was supposed to. And this is what gives funders, landowners, and reviewers measurable evidence that the work matched the prescription. Okay, so time for one last little video. This one is a little over 5 minutes, but this is one that all of you are going to be able to understand and note that this is the type of platform which any of you can interact with. You can even use this on your phone. Okay, so yeah, in this video, you'll see how you can interact with drone imagery in a cloud platform. And yeah, we're going to start here at the emergency animal shelter at the Girl Scouts. And yes, those are horses. So we have an immediate situational awareness. We can see structures, access routes, nearby vegetation, open areas in the broader setting around the shelter. Turning on the polygon layers helps the image become more than just an image. Layers can represent infrastructure, treatment areas, or other assets that need to be tracked. So now we're looking at the vegetation around it. That's where I turn on the EVI layer so you can interact and see with this on the platform. All right, so I'm going to turn this off and then turn on the digital surface model, or DSM, which represents the elevation of the visible surface, trees and structures. So as I adjust the elevation display, you can see lower and higher areas begin to separate visually. For forestry work, that matters because topography influences water drainage, fire behavior, and vegetation patterns. And so when the DSM fills in, we're essentially adding another layer of understanding. So another practical feature is creating an elevational profile along a road, trail, cut bank. This could be a water course. You're delineating WILPA's boundaries. Um, but in this example, I drew a line along the road surface, and Pix4D automatically generates the elevation profile, calculates the 2D and 3D lengths, the minimum and maximum elevation, and slope, which you can toggle between percent in degrees. See that as that changes along the dot on the road as you go. And then next we'll measure the cut bank profile. So for forestry work, this is useful because slopes can affect access, equipment feasibility, erosion risk, drainage, road maintenance, fire line construction. Instead of describing a road segment generally, we can measure it and document it directly in a cloud environment. So what we're seeing is an aerial view of some vegetation that was piled by machines, and using the volumetric analysis will allow land managers to precisely quantify the volume of biomass in piles. By applying the 50% rule for dry mass carbon storage, these specific volume measurements can be converted into high accuracy carbon sequestration data rather than relying on broad estimates. As a side note, about half a plant's dry weight is stored carbon. It's this level of granular monitoring that directly supports the 2018 Forest Carbon Plan by providing the verifiable data needed to track progress towards the state's 2030 and 2050 greenhouse gas reduction targets. So this view is a 3D photogrammetry model created from a flight last year. So we're starting at the helicopter pad at the Girl Scouts. And even you can make up my Tacoma pickup and the drone case just above it. It's all recreated from photos. So as I zoom out and tilt into 3D, the value shifts from detail to situational awareness. Now we can see the landing pad, roads, open areas, buildings, and how the surrounding vegetation all relate to one another. As the camera pans across the site, the model gives us a quick sense of access, terrain, canopy structure, vegetation density. For forestry, fuels, emergency planning, or land stewardship, this context really matters. It's useful because it lets people who may never visit the site still understand the landscape in 3 dimensions. It turns a project from a flat map into something managers, partners, and funders can explore and discuss together. So this is how drone imagery and map buffers can support defensible space planning. We start by identifying the structure itself. Then we can create distance-based zones around the building, beginning with the first 5 feet, and then expanding to 30 feet, and then finally out to 100 feet. So for the homeowner, this makes defensible space easier to understand. Instead of reading a regulation or guessing where these zones fall on the ground, they can see the zones overlaid directly on their property. For an insurance auditor, agency reviewer, or fire inspector, this creates a visual and spatial record. It shows the structure, the defensible space zones, the surrounding vegetation, and the condition of the property at the time of the flight. The value is that both sides are looking at the same evidence. The homeowner can use it to plan and document work, and the reviewer can use it to verify conditions more clearly. It turns defensible space from a vague conversation into a mapped, measurable, and repeatable record. Okay. So we touched on this earlier, but just to kind of give you a zoomed in idea of what we're seeing here, this is a digital surface model, or a DSM. It's a 3D representation of the Earth's surface That includes all objects on it, including trees, like this coulter pine. A DSM captures the top layer of the landscape exactly as a sensor sees it from above. Unlike LiDAR, which uses expensive laser pulses to see through gaps in the canopy, this DSM ortho is generated using photogrammetry, so photos, which is far more cost effective and provides a high resolution, full color visual display record of the forest. This method captures the exact outer shell of the vegetation with incredible detail, making it superior for quickly calculating the volume of top-heavy fuels and surface biomass. We can fly more frequent missions to monitor growth and fire risk without needing a federal agency's budget to get the job done. And you can just see on the right how the color changes. At the very top of the tree, it's dark orange, and how the gradient changes to a lighter orange and into a yellow, just highlighting the elevational change of the tree. Okay, the long-term record is where this program really starts to separate itself. A single image or a single field season gives us a snapshot. Repeated monitoring is what gives us a trajectory. Over time, we can track how individual trees and stands respond to drought, treatment, pests, and fire cycles, not just whether something changed, but when it changed, how fast it changed, and whether that change was sustained. That matters for management because forests do not respond on a clean schedule. Some responses are immediate, some take years to show up. Long-term monitoring, though, will help us distinguish short-term fluctuations from meaningful ecological response. It also creates something extremely valuable, a structured time series of tree-level data. That kind of data set is eventually what makes stronger predictive modeling possible. Not probable, possible. At the broadest level, PSMP works across 3 stages and helps answer 3 practical questions. What was there to begin with? What changed? And can we verify that change with confidence? This slide shows the cadence I envision for long-term deployment. The drone side can happen as needed, depending on management needs and budget. That gives us a frequent, repeatable observation of canopy condition and tree spacing. Traditional forestry measurements happen less often. Those are the years marked with an asterisk. And that's because field-based measurements are slower and often designed around longer remeasurement intervals. The strength of PSMP is that it combines those 2 tempos, more frequent aerial monitoring with periodic traditional field measurements. That way, we're not waiting 5 or 10 years to understand whether something is happening. We can monitor continuously, then anchor those observations with periodic field data. Over time, that creates much stronger monitoring record than either method would on its own. The final phase is integration. After enough repeated monitoring, we're no longer just collecting images and field data, we're building a longitudinal data set. That means imagery, individual tree mapping, spatial structure, field physiology, treatment history, and repeated observations through time all start to live in one system. Once that happens, we can move from describing what happened to modeling what may happen next. That is where predictive analytics and AI become useful, not as a replacement for field judgment, but as a way to recognize patterns across years of standardized data collection. Partnership is where PSMP goes from here. I'm looking for pilot programs with tribal governments, agencies, universities, nonprofits, private landowners, and funders who want to build long-term forest health records. Different organizations may use PSMP differently. Agencies may need treatment verification and defensible reporting. Tribal governments may use it to support land stewardship while maintaining data ownership and sovereignty. Universities may use it to build research data sets. NGOs, landowners, funders may use it to document outcomes and communicate impact. But the common thread is the same: consistent data collected through time using a standardized methodology. That is what creates the foundation for AI-ready decision support. Real models trained on repeated imagery, field measurements, treatment history, and observed tree response. 10 years from now, the most valuable organizations will not be the ones trying to recreate the past. They'll be the ones that already have the data. And so this is the final slide that I'm going to show you. But it was this single image I was looking at in January of this year when I was about halfway through the Polygon project. You can see not every tree is even identified yet. But I was reminded of a story Cliff Devers from PalmEd told me about the creation of the Lucenio creation story. And he talked about a time of interconnectedness when the world was soft, everything had a voice, the trees, the rocks, the dirt, us, everyone spoke a common language, but then that world changed. And when I was thinking of that story and literally had this same frame up on my computer, the idea really clicked with me. So in my interpretation, it felt like a lost dialogue had been reestablished, that the land was becoming readable again. The orange trees are signaling or speaking of stress. There's too much competition, not enough resources. The response was a direct silvicultural treatment, so thinning, and even 2 months after treatment, on the upper part of the screen, we can start to see a different response. The Quilla, the California black oak, are telling us that they're a bit stressed due to the increased heat and wind that they're experiencing. The green trees on the right are telling a different story: fuller crowns, better access to resource, and these Quilla are saying, we are resilient. So in closing, I just want to say that PSMP does not give the forest a voice because the forest already has one. It simply helps us learn how to listen. And with that, I'm going to turn it back over to Kara.
Thank you, Kevin, so much. I really appreciate you sharing all of this information, your knowledge, your experience, and mostly just sharing your time with us. And just really appreciate this opportunity to work with you over the years and get to know you. And yeah, just nerd out with you. So thank you so much. In regards to questions from the audience, there were a few that were already answered in the Q&A. Thank you for those questions and individuals who are wanting to share the recording with their network. But there was one question in the group chat from Robin. Was it Robin? Yes, Robin. Did you explain what treatments were being used against GSOB?
Oh, primarily it's thinning and masticating. So thinning out the unhealthy trees through low thinning, so the lowest vigorous, least healthiest trees get removed, as does a lot of the brush on the ground. So they do that, it takes a couple years for the trees to expand their lateral root system and develop a thicker, lusher canopy before they can respond. But yeah, that's what they do. So once that tree starts growing faster, it becomes more resilient, and they're not really sure what is this actually driving GSOP out? Who knows? But I think the results are pretty obvious, because we can't quantify that. There's a lot about GSOP we still don't know, but it seems like when the trees are healthy and growing fast, GSOP has a much more difficult time thriving.
Thank you for answering that. Another question, could satellite imagery be used for comparison instead? Example, via QIS.
Yeah, in Q, satellite imagery is functionally blind to the physiological state of a tree. These resolutions that I'm working with are sub 2 inches. whereas satellite imagery is 10 meters, so 33 feet. So, yeah, it would be really difficult. Comparing a broad landscape, the 600-acre footprint at the Girl Scouts, that absolutely could be done. But for individual health monitoring, that may be really difficult.
Thank you. And another question we have from an individual named Derek. It'd be interesting to know a little bit more about your approach to detecting and delineating individual tree polygons.
Yeah, there's definitely a method to the madness there. I don't get into too much of it because I know I've really developed it's been a lot of hard work to get to as far as where I'm at, but it's a combination. Again, it's not just one single image. Trees change through time. What there's signals in right now, March, April, and the spring look radically different than they do in the summer and in the fall. So by overlaying those layers and looking at the individual changes in the trees, that helps me differentiate between tree crowns as well. There's also, there's also some sleuthing, some, that goes into it because you have to understand too, especially when I see an overlapping canopy, I can't always make that polygon as wide as I want it. My method though centers on trying to capture at least the upper third of every canopy because that's where a majority of the tree's productivity takes place. But yeah, there's some give and take and yeah, that goes along with that. And then trial and error too, looking at the results has helped a lot too. And then I do segment the rasters as well. I didn't get into that at all, but doing raster segmentation helps to separate those individual canopies as well. And then, of course, I mean, I'm not going to lie, the work we did at Palma, we digitized over 10,000 individual trees. But that required several ground truthing trips as well out there. But with being, Palma is definitely managing the land. I always say I manage the data that represents the land. So when I go up there for site visits or whatever, I usually have an events and map prepared, and there'll be certain areas of the project area I'll go out and scope out on my own to make sure I've got the GIS environment reflects the reality on the ground.
Thank you. And from Paul, what is a ballpark estimate per acre for remote sensing capture?
Sorry, I completely missed it. I was reading a question.
Oh, it's what is a ballpark cost per acre for remote sensing capture?
Holy smokes, that fluctuates widely. It really depends on, access to the site, how big the site is, what, resolution you're looking for. That depends on whether I'm just turning over a raw product or if I'm doing all of the GIS work as well. And
Thank
Emily, I see your question. Yeah, synthesizing traditional field data. Right now, it's in a relational master geo database. And those, again, a lot of the PSMP has been developed over the last few years. It's really in the last year that things have started to come full circle and having these multi-temporal data sets to show not only funders, but the people that I work for, like this is a valid way to start tracking projects. So a lot of what I've been developing in the background has been brought up to this point, and only in the last well, actually the last like several weeks, I've been in touch with Esri and hopefully getting enveloped into their partner network. I was with government relations for a while. Now I've been in communication with their tribal nations account manager. So I think they're trying to find a good fit for me, and then how we can take this idea and really solidify it in a GIS environment. And
thank
then
you.
I
And just
saw, oh,
Oh,
go
just
ahead.
for recording purposes too. So Kevin's response just now was to the question, can you speak to how you synthesize drone data with traditional field data? Are there specific metrics you have found that align the best? So that response was for that question just now.
Yeah, yeah. Just kind of doing it, the way I know how to do it. But I'm sure there's other ways, much higher level ways of doing things. I'm not quite into R and any programming. I can filter shadows and some of the basic stuff. But yeah, with the pilot projects, really looking for someone to help me scale this out. And Kent Drake, I see he's on this call. He's the land manager out at the Girl Scout camp. And yeah, he said the drone work has allowed us to walk the forest and pinpoint specific areas that need treatment, which is exactly what they're doing, that type of precision forestry. And yeah, the
Amen.
working with the tribes, I absolutely love it. Working out at the Girl Scout camp kind of gives me my own temporal data sets that I can use, work with, and share with on a broad audience. But even to the Girl Scouts, the reason why I featured it, the Girl Scouts today is because they have a very diverse landscape, as you saw, open areas, treated areas, untreated areas, pest infested trees, structures. So it for you folks for the demonstration, it really, I think, gave the best view possible of what can be done.
Thank you. Kara, have we missed any questions in either of the chats? No? All right. Well, if any questions come up, feel free to email us, and we can get the question over to Kevin, and have him respond to you. But we really appreciate you all joining us. We really appreciate you, Kevin, and all the knowledge and experience you've shared with us. We look forward to continuing to see just how your work evolves and the communities that you'll be working with, and yeah, more about this technology. And in the chat, we've placed Kevin's information, website, email, LinkedIn, as well as the Esri contact, Heston Smith, and their email. And if you could, if you haven't already, please subscribe to our newsletter at the Climate Science Alliance. We provide information on a monthly basis, regarding, webinars, trainings such as this one, opportunities to get out on the land together, funding opportunities. We do put a lot of information out there. And we are also on social media, under the Climate Science Alliance. And yes, we just appreciate you all joining us today. And please do not hesitate to reach out with any questions. And we hope that you have a good rest of the week. So take care and thank you.